Hello everyone, welcome back. In this video we'll be taking a look at order limit theorem. So the order limit theorem is another useful theorem for us. It says that if all the terms in the sequence are positive, if all the terms in the sequence are greater than or equal to 0, then the limit itself is greater than or equal to 0. And the second property says that if a sequence an is less than or equal to bn, then the limit of the sequence A is less than or equal to the limit of the sequence Bn. And if all the terms in the sequence are less than a number C, then the limit itself will be less than the number C. So let's go ahead and prove these theorems. So the first one says if an is greater than or equal to 0, then all the limit itself is greater than or equal to 0. So remember that the sequence an tends to A. So we need to show that an is greater than 0, then A is greater than or equal to 0. So suppose for contradiction, we're going to do a proof by contradiction. So when we're doing a proof by contradiction, we always assume the first part and negate the second part. So suppose for contradiction, that A is less than or equal to A is less than 0. Since the premise is A is greater than or equal to 0, the negation will be A is less than 0. So assume an is greater than or equal to 0, and since we're doing contradiction, we assume the opposite for what we want to prove, and A is less than 0. So we're gonna choose epsilon. So let epsilon is equal to minus A. Remember, epsilon always has to be positive, and remember A is negative in this case, and since we're choosing a negative of a negative number, so that's a positive number, so epsilon is positive. So we seek n such that an minus A is less than minus A for all n greater than or equal to n. So this can be rewritten as an minus A is then minus A and A. So if we take this to this side of the equation, we get an is less than 0. And this is strange, this is a contradiction, because we just assumed that an is greater than or equal to 0, yet we are getting that an is less than 0. So this, what we assumed, is not possible. So what we assumed that a is less than 0 is not possible. So our contradiction is because this contradicts. Therefore, when an is greater than or equal to 0, the limit of an, which is a, is also greater than or equal to 0. And we are done with the proof. So let's go and prove the second one right here. So the second one says if the two sequences such that one sequence is less than the other sequence, the limit of the sequence A, the limit of the sequence an is also less than the limit of the sequence bn. So I'm going to write an is less than or equal to bn as bn minus an greater than or equal to 0, and the limit of bn minus an is equal to b minus a. This is from the algebraic limit theorem that we did before, which said limit of bn plus an is always equal to limit of the sequence b plus a, and replacing the minus doesn't really change that. So we're going to use the algebraic limit theorem to show that the limit of bn minus an is also equal to b minus a, and we're now going to use the previous theorem to show that b minus a is of course greater than or equal to 0, because since bn minus an is greater than or equal to 0, And from the previous theorem, we showed that if an is greater than or equal to 0, then the limit is a greater is greater than or equal to 0. So if bn minus an is greater than or equal to 0, the limit b minus a, which we know exists because of the algebraic limit theorem, is also greater than or equal to 0. And b minus a greater than or equal to 0 can be rewritten as b being greater than or equal to a. And that's what we wanted to show, and we're done with the proof. So the proof of the third property of the order limit theorem is pretty similar to the one we did right here. So I'm gonna let you guys do that on your own as practice. So hope you guys enjoyed this video. See you next time.